All right, supporting null results. Going way back to the start of the semester, when we talked about null hypothesis significance testing, one of the points I kept making was failing to reject the null hypothesis doesn't really provide support for null results. So let's take a look at an example. Here is an example we saw in the power slides. It's a new educational technique. We have defined a meaningful difference as 2 points, a 2-point difference on a 3-point exam. And our power analysis suggested we needed 100 participants. Let's say we went ahead and did this study, and we end up with a result that looks like this. Our confidence interval ends up going from about -4 to about positive 2.4, meaning that 0 falls inside of that confidence interval. We can't rule out. We cannot rule out 0. So we fail to reject the null hypothesis here. Is that evidence? Does failing to reject mean that the programs are equally effective? Definitely not. Or as I've written here, oh, hell no. The literature is full of interpretations suggesting non-significant effects support the null. That's a misunderstanding of significance testing. Just because you see it in print doesn't mean that it's right. Another interpretation here is sometimes you'll see people pointing to large p-values as indicating support for the null. Again, a large p-value doesn't tell you anything. We have no way to support the null using the procedures that we typically use, but that doesn't mean that there's other approaches out there. One approach is called equivalence testing. With equivalence testing, we can specify the size of a scientifically or substantially important point, or what I called a meaningful effect. Here it's commonly called the COC, the smallest effect size of interest. And we can use these approaches not to get at statistical significance, but to get at what we're defining in terms of practical significance. Is the effect big enough to matter? I would definitely recommend taking a look at Daniel Locken's blog post on two one-sided tests, or the TOST approach here. What we do with the 2 one-sided tests is we examine the lower boundary and an upper boundary. So if my difference of interest is a 2-point difference, I'm going to look for -2 on one end, +2 on the other end. If I can rule them both out, then I can say, hey, the difference is obviously not a 2-point, is unlikely to be a 2-point difference in the population. All this are independent samples T's with non-zero values for the null hypothesis. You can see how we could calculate this by hand, and we could get our 2 different T values. We see that one of them is going to allow us to reject that T of 4.2. T of 1.4, probably not. You can see I've got a 95% confidence interval for one of them, or 90% confidence interval for one of them. And you can see that this confidence interval includes that value of 2. So that tells us we can't rule 2 out. We don't have evidence for equivalence. The TOSTER package performs this nicely for us. You can see the different results it gives corresponding to our values. You can see the boundaries. It even draws you a nice graph. And it's showing you where the ends of the confidence intervals are. This gives the TOST one is the one we want to look at. When that is non-significant, we do not have evidence for equivalence. We want to be excluding 2 on both sides with our interval, and we don't exclude 2. Interestingly, this is not a new idea. Daniel Lockens is incredibly good at highlighting techniques that are useful but are not used by anyone, and that happened to fall right into where I was with my presentation of these approaches. In my book on power, I had a section that focused on supporting null hypotheses, and the procedure that I suggested was a confidence interval around the standardized mean difference to see if you could rule out that effect size of interest. And that's what I've got here using the MBEST package. The confidence interval does not exclude my value of 0.4, so I would fail to reject. Same approach, same exact results. Daniel Lockins just marketed it better. Another value we can use, and one that we've seen before actually, is the Bayes factor. There's two different Bayes factors values. There's a Bayes factor 1.0 and 0.1. 1.0 addresses the strength of evidence of support for the alternative over the null. So you can think of that 1 as alternative, the 0 being the null. And then values BF01, values greater than 1, give support, greater support for the null in relation to the alternative. Most of the output that we see comes in the form of BF10, but to get BF01, you just have to take 1 divided by BF10. So no BF deal. Ha ha ha, statistics joke. So you can see I've done this. It gives me my value that is, of course, in 1,0 form. I take 1 divided by it. It gives me a value of 0.76. What is that telling me? It's telling me we don't really have a heck of a lot of evidence for the null hypothesis. You can see how Bayes factor values are interpreted. If we take a look at these are 1.0 values, my value of 1.32 is actually anecdotal evidence for the alternative, no evidence for the null hypothesis at all. So we don't really have support for the null in this case.